Let's take a look at how ping actually works. So for this, I'm going to ping the Google DNS, which is 8.8.8.8. One time is enough. You can see that we got a reply. We got 32 bytes of data. We have the time that it took for the reply to come in. While I ran ping, I had Wireshark open in the background, sniffing the network traffic, and I have it filtered here on ICMP. So I actually have the two packets that it sniffed. I have the ICMP echo request and the ICMP echo reply right over here. So when ping actually starts, it starts with sending a request to the server that you're asking. In this case, it sent the request to the Google DNS, and afterwards I got a reply from the Google DNS back to my IP address. You can see on the left side we have the packet in human readable form, and on the right side we have the binary representation of the packet. So this is the actual bytes that are sent on the line. Let's open up the Internet Control Message Protocol section. This is actually mostly shortened to ICMP, and this is the protocol that ping uses to actually work. You can see that the first field is actual identifier of the type of the message. ICMP supports a lot of different kinds of messages, but ping only uses the type 8, which is echo request, and type 0, which is echo reply. We're going to look at that soon. The code in this case is always going to be 0. Ping only uses code 0. Checksum is the calculation of the checksum of the ICMP section of the packet. This can actually help make sure that the line is reliable and there's no information loss. Afterwards, we have the identifier and the sequence number. Both are actually used to identify the request. So when the replies come back in, ping knows which reply is relevant for which request. So as you can probably guess, every reply for every request has the same identifier and sequence number. That's how ping knows that the reply is relevant for the request that it sent. Notice that we have also for identifier and also for the sequence number. Wireshark shows us the big endian representation and the little endian. That's B and LE. The difference between big endian and little endian is that it orders the same number in two different ways. So in big endian, you look at the number from left to right. So in this case, 1 is going to be 0001, and little endian is going to be the same number. You can see that didn't change when I pressed on it, but you're going to look at the number from right to left. So in this case, it's going to be first the 01, which is on the right side, and then the 00 on the left side. Same thing for the sequence number. Here it makes sense to actually look at the big endian, since also the identifier big endian is 1 and the sequence number is 1. This is actually the first ping that I'm sending after restarting my computer. Finally, we have the data, which is afterwards. You can see that it's just a bunch of letters. This is the actual 32 bytes that ping was talking about when it told us it sent 32 bytes of data. So this data is actually just a bunch of random bytes that you can include in your payload while sending the ping request. Now let's take a look at the ping reply. So I'm just going to press on it. You can see that it looks pretty similar, but this time the type is not 8, it's actually 0. So this is the type that identifies an echo reply or ping reply. Code is also 0, and the checksum is recalculated because the type has changed to 0, but everything else is the same. So we have the same identifier and sequence number, and the data is also the same. Stay tuned for my next video, which will be actually making a simple ping utility in assembly. Subscribe for more videos, and thanks for watching.